Carly McAvoy, back to do your homework 3B video. And we got 26 questions, so let's get started. This is describing and comparing data. They're asking you to find the range, the variance, and the standard deviation. If you have not done the video for 3A, you may not know how to do this, but if you did the 3A video, you know how to do this already. This is picking up where we last left off. When I wrote these homework assignments, I think I really wanted you to get that down. So anyway, you're going to take your highest value and subtract your lowest value. The highest value in here is 4, the lowest is 1, so that would give us 3 for a range. Now to find the variance, you take the square of the standard deviation. So you're going to take the standard deviation and get that on using your calculator, and then take that to the second power to get your variance. And that's going to be that. So is the decrease of 4 miles per gallon unusual? Why or why not? This, you have to read the whole thing, but fuel consumption is commonly measured in miles per gallon. An agency designed new fuel consumption tests to be used starting with 2008 car models. Listed below are randomly selected amounts by which the measured MPG ratings decrease because of the new 2008 standards. Find these. And is the decrease of 4 miles per gallon usual or unusual? So what I want to talk about here is standard deviation for a second, and just explain to you what that means. So I guess we should do this so I can answer that. I think this does go a little further than the last one, actually. So the last things that we were doing. So let's jump over to mine and do those, and then I can explain something that's important that I almost just kind of skimmed over. So let's see, in my haste. We can use either calculator. I'm going to use the 36X Pro, and I have to enter all of this data. So I'm going to do this on and then on clear to get that cleared out, and then I'm going to enter my data. And I have 1, 1, 3, 2, 3, 2, 4, 2, 2, 2, 2, 2, 2, 2, 2, yep. 1, 1, 2, 2, 3, 1, 2, 2, 2. So according to this, I should have entered 20 pieces of data. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I got them all entered. And now I want to find the range. Well, on this one again, the highest value I had was 4, and the lowest value I had was 1. So hopefully you can see that that's just going to be 3. All right. Now the variance of the sample, I'm going to do this second function data and one variable stats here. I'm going to hit enter. I have my data in L1. I just have one of each one of those. Actually, I have more than one, but I've just counted each one as one single data spot. And then I'm going to hit calculate. And so I have 20 things, and my mean is 20. That's the average is 20. My S of X here is 0.7947. That's my standard deviation. Move this over. So it's 0.7947. And they asked me to round to 1 decimal place. So I'm going to round that to 0.8. But when I do the variance, I'm going to take this to the second power. It gives me more accurate if I can kind of hang on to that for a second. So second function quit, and then I'm going to do, man, sorry, I'm jiggling this around so much, 0.7947, the whole thing squared. And that gives me 0.6315, But because they asked me to round to 1 decimal place, I'm going to call that 0.6. All right, so my standard deviation is 0.8, and then my mean, remember when I did that, I didn't write it down, but I'm going to tell you now, my mean was 2. So let's talk about this for a second. This is how they got 0.8, 0.6, blah, blah, blah. Okay, so if I have a normal distribution, then I have this, I'm not really loving this, I have this bell-shaped thing, right? And in the center at the peak is my mean. So this is the place where the mean is, which is x bar, all right? And so I know that that value is 2 because I just saw that on the calculator. And what a standard deviation of 0.8 means is that if you go over here to 2.8, or if you go back here and you subtract 0.8, so that's going to be 1.2. Do you see where I got that? That's 2 plus 0.8, 2 minus 0.8. That's one standard deviation to the right and one to the left. My drawing's not exactly that accurate, but you get the idea. And if I go one more out here, and I get 2.8 plus another 0.8, I get 3.6. And if I come over here, see, that should be the same. My drawing is pretty crappy, but anyways, I hope that you're with me here. If I come over here and do one more, then I subtract 0.8 from this, which is 0.4. And so I'm 2 standard deviations away here. This is 2 standard deviations. And this is also 2 deviations away, right? 2 to the left, 2 to the right. So 2 standard deviations on either side. When we fall between 2 standard deviations, either to the left or the right, we say that that's the usual values, right? Anything between these 2 points are what we call usual values. 2 standard deviations to the left, 2 standard deviations to the right. My drawing is hideous. I almost feel like starting over, but I don't want to. So anything out here, these are unusual values. And these are unusual values. It turns out that if we look at this, 90% of the data that we get will fall within 2 standard deviations. And the other 10%, the 5% on either end, those are considered unusual. So when it's asking, is the largest decrease 4 miles per gallon, is that unusual? Well, 4 would be out here past 3.6. So it would be yes. It's unusual because it's more than 2 standard deviations from the mean. That's what makes it usual or unusual. Okay. If I had a difference of 0.2, that would be unusual also. If I had a difference of 3, then that would not be unusual because it would fall within the 90% range. All right. So that's what we're always looking for. Is in the 90% range? Cool, right? All right. It's kind of neat. Something kind of new to look at. Alright, so now we want to calculate, where's a piece of paper here? Calculate the coefficient of variation for these 2 things and for each of the 2 samples, and then compare the variation. Okay. So the coefficient for variation for the amount collected by the security service company is something percent. When we have, let's read the problem first. Listed below are amounts in millions of dollars collected from parking meters by a security service company and other companies during similar time periods. Do the limited data listed here show evidence of stealing by the security service company's employees? So what we're trying to do is to compare these variation for each one and then decide whether it looks like one of them is being deceptive. Okay, so let's come over here to the computer and take a look here for a second. Okay, so I'm looking up here and I see these values and I think they are the same. No, they're not the same as mine, is what I had, but anyways. The coefficient of variation is a very simple formula. You're just going to take the standard deviation that you know how to find and divide by the mean. We can look at an example over here. If you had this, you put in all your values, and then whatever you get for S, which is your sample standard deviation, you divide by the mean that you get, and then you times by 100 to get the percentage. And then you do it for the second one. You're not going to do all that. You're just going to use your calculator. Heavens, you're not going to be doing that all on your own. But anyway, you're going to do that in your calculator, and for the first set of data and for the second set of data. And then you find the standard deviation, which you are not going to go through that process. You're going to let your calculator whiz those out at you as off, whiz them out, figure it out for you. Awful process that we used to have to go through, and now we don't have to do that. So now once you get those two, you take your standard deviation and you divide by your mean and you times by 100, and you get these two values. If you do it for the first one, you do it for the second one. And we've already seen how to calculate standard deviation on the calculator, how to find X bar on the calculator. And so the only new thing here is to divide those two things and then multiply by 100 to get it in percent form. And then the next thing they're going to ask you is that, you know, you look at the two values and say, like, does it look like one of them is maybe stealing? The difference of greater than 1% is significant, and this is huge. So somebody is not being completely honest. So that if yours were within a 1%, you would say they're fine. If they're not, then you'd want to be checking into that. Okay. So it's a little bit different use of something that we've already had. All right, so let's take a look at this one, number 3. We'll jump over to my paper and do mine. For real. Let's jump over. Cover up the answers. A certain group of test subjects had a pulse rate with a mean of 77.2 beats per minute and a standard deviation of 13.1 beats per minute. Would it be unusual for one of these test subjects to have a pulse rate of 83.4? So we can draw the picture again. I'm going to draw it just because I think it's nice to kind of keep putting in your head what we're talking about. When we're talking about a normal distribution where here's your mean, X bar is right there. Then if we go one standard deviation over, we have X bar plus a standard deviation. Over here we have X bar minus 1 standard deviation. And if we go over again, we have X bar plus 2 standard deviations. And over here we have X bar minus 2 standard deviations. And these are considered the usual values, right? Anything in here is usual. So our usual values, and that is considered to be 90% of the population will fall within 2 standard deviations to the left or 2 to the right. So all we have to do is take our mean, which is 77.2, and subtract 2 times the standard deviation, and our mean 77.2, and add 2 times the standard deviation, and we would see what are those ranges of values. So 77.2 minus 2 times 13.1 is 51, and 77.2 plus 2 times 13.1 is 103.4. So those are the range. If your answer that you're asking about is in that, 83.4 is totally usual or normal, right? Because it's in the range. So it'd be yes, it's smaller than the minimum. Wait a second. No, it's between the minimum and maximum usual values. This is the minimum, this is the maximum, and our number is fine. Okay, let's go on and see what we get here. Find the standard deviation S of sample data summarized in the frequency distribution table below by using the formula below, where X represents the class midpoint, F represents the class frequency, N represents the total number of sample values. Also, compare the computed standard deviation to the standard deviation obtained from the original list of data values. Yucky, so we don't want to do that. we want to just use our formula that we know from the calculator. But we do need to know that what the midpoint is, right? So if we have 30 plus 39 and then divide by 2, we get 34.5. Now you can see if you subtract your lower class boundaries, 40 minus 30, that the class width is 10, which means that your midpoints are also going to be 10 apart. So I don't have to do any more calculations here. I know it's going to be this. Whoops, that's a 4. It's being really sort of sloppy today. I don't know what's going on, but hopefully you can override my inadequacies. So that's what I'm going to put into the calculator, and then I'm going to put the frequencies that go with that into the calculator. And we did that on an earlier problem, I think, in the previous homework, so we know how to do it. I'll use the TI-84 for this. Let's go here, and I'm going to edit or clear this, clear, enter, and put 34.5, 44.5, 54.5, 64.5, 74.5, 84.5, 94.5, and then over here I'm going to put in, I'm going to clear that, and I'm going to put in my frequencies, which was 1, 2, 5, 2, 10, 30, 35. And then I'm going to calculate that by doing stat, calc, one variable stats, and here I'm going to tell it, well, I have my data in L1, comma, and my frequencies in L2, and I'm going to hit that. And what I get is 83.68 for the mean, but they're asking me for sample standard deviation, I think, in this problem. So I'm going to get, to rent one place, I'm going to get 13.6. You can see S of X is 13.55, and so I'm going to get 13.6 there. I don't think you should do any of those long calculations. Use your calculator, that's the point. Consider the difference of 20% between two values of a standard deviation to be significant. How does this computed value compare with the given standard deviation of 11.1? Well, if you take 13.6, first of all, let's figure out what is 20% of 11.1, so I can see how much greater it should be, right? So 11.1 times 0.2 is 2.22. So if it's more than 2.22 different, then it's significantly different. So I'm going to take 13.6 minus 11.1, and that's going to show me 2.5. So the difference is 2.5, and that's more than what we found to be 20% difference. So it is significantly different. Okay, and that's because they gave us the 20%. So I figure what 20% of my value is and see if what I got was more than 20% or not. All right, number 5. Heights of men on a basketball team have a bell-shaped distribution with a mean of 172 and a standard deviation of 8. Using the empirical rule, what is the approximate percentage of the men between the values of 164 and 180 centimeters? Empirical rule tells us this stuff. And my drawings are not so cool, but if I have a normal distribution, there's my mean, this should come straight down. If I am one standard deviation to the left and one to the right, the empirical rule oh, it's 95. Heavens to bid. I drew something on there earlier that was wrong. Darn it. It's not, I don't know what I was thinking. If I'm 2 out, I'm 95%. Right? Okay. crippity cripes. Now I've said that and it's lasting forever. I'm not redoing this. So just remember 68, 95, 99.7. So if it's one standard deviation out, it's 68% out. If it's two standard deviations out, that is 2 to the left or 2 to the right, it's 95% of the population is covered. Ugh, it's going to haunt me that I said 90. And then if I go out 3 standard deviations, then I'm going to get the 99.7% of the population in there. So I'm trying to figure out if these numbers are 1, 2, or 3 standard deviations out on this problem. So the mean was 162 and the standard deviation 172 and the standard deviation was 8. 172 plus 8 is 180, and that's where we're at here. If I say 172 minus 8, I get 164, which is that one. So that these are just one standard deviation to the left and the right. So that's how I get 68%. One standard deviation is 68%. If I add another 8 to that, which is another standard deviation, I go up to 188. And if I subtract another 8 from that, I get down to 156. So that means that to get to these numbers, I move 2 standard deviations to the right, 2 to the left, and so that's 95%. 95, 95, 95. Don't remember the 90 thing and miss it on the test because of me. So that's what we're looking for there. If they did another 8 on there and 196, then you'd talk about 99.7%. Okay. I think this one you could probably do now. Heights of women have a bell-shaped distribution with a mean of 161 and a standard deviation of 5. Use Chebyshev's theorem. What do we know about the percentage of women with heights that are within 2 standard deviations of the mean? What are the minimum and maximum heights that are within 2 standard deviations of the mean? Oh, so Chebyshev's, that's how I say his name. Could it be? I don't know. It's different than the empirical one. It's another one that uses that. So let's go take a look at it. His is different enough that I want to make sure that I don't remember it incorrectly and throw you again. You can always go to view an example, and it should show you a picture. Anyway, they don't. 3 standard deviations are 89%. So let's draw that picture. Here's the mean. Here's 1 standard deviation. Here's 2 standard deviations. Here's 3 standard deviations. That would be, he's saying 89%. They're asking about 2 standard deviations. So let's go look at the book. It looks pretty blank. I don't think that's going to work. So it should just be 1 minus 1 over k squared. 2 standard deviations away is what they're asking on this one. So 2 standard deviations may be 1/4. 1 minus 1/4 is 3/4, or 75% of the data would be 2. That's how you could calculate that. Let's see. If that's right. They did it for 3. We could do it for 2. 75. Yeah. So I just couldn't remember what his numbers were. So 75% of the data between 2. This is not something that comes up often, obviously. And then the second part asks you to find what the height is within 2 standard deviations. Again, you're just going to be adding the mean twice or subtracting it twice to find those rules. I mean, look at the notes that I give you, and I'll go over this. I can't. Yeah. Anyways, that's kind of kooky. I should probably take that off. But anyways, I've got on this. There'll be only one question about that. Okay. Number 7, which measures of variation are very sensitive to extreme values? Well, a histogram is not even a measure of variation, so forget about that. The variation, the range, talking about how much do the very smallest and largest change. And yeah, so these aren't even variation measurements. Mean and median are measures of central tendency, right? So those are the central measurements. So really just the range is the only one, and it's very sensitive to that because you're only looking at the very highest and the very lowest. So if you have extreme values for that, it's just going to throw that off wicked. So that's why we don't like to use range very much. Which of the following is not a property of the standard deviation? The standard deviation has, let's talk about it. The standard deviation is a measure of variation of all data values in the mean. That's a good definition of it. It's a property of it. I would say that's pretty good. The value of the standard deviation is never negative. That's true. We can go to the left or to the right, but we still talk about one standard deviation left or right, one standard deviation left, two standard deviations, but we don't talk about them as negatives. And when we do want to talk about them as negatives, we call them z-scores. So they're still a standard deviation, but when we put a sign, attach a sign to them, they become z-scores. The units of standard deviation are the same as the units of the original data. That's true. They have the same unit. Variation is that unit squared. That's why variation is a little weird. And then when comparing variation in samples with different means, it is a good practice to compare the two standard deviations. Now, if you have different means, then your standard deviations don't mean the same either. So you don't want to compare those for two samples. So that's bad. I think that's the one that we should be choosing. That we don't like to compare those when they have different means. Okay, so let's see. For data sets having a distribution that is approximately bell-shaped, what is it that states that 68% of all the data values fall within one standard deviation of the mean? Well, we just did that, and that was the empirical rule. That was the one that I messed up the middle data, which is 95, 95, 95. So it's empirical is that one, the 68 and then 95. The square of the standard deviation is called variation. We've been doing that repeatedly. Whoa. I want to try again. I want to try it again. Sorry, is the variance. Sorry, I said variation. We've been doing that repeatedly, but apparently it didn't stick with me. The variance is the square of the standard deviation. The variation is just how much is the data varying, Hey, you don't have to be perfect at math to be like it or to be good at it. And, when you do these videos, well, you're never going to do them probably, but when I do these videos, I do have a chance to go back and edit and take out, take out things that I get wrong. But I think, I think sometimes it's good to see people make mistakes. People make mistakes with math. That's part of it. You make a mistake, sometimes you learn more from those mistakes than from doing it right. So I kind of like you to see the mistakes, even though, in truth, there are times when I go and take something out because it's like, oh my gosh, that's going to make them so confused. And I try not to leave those kind of mistakes in. A little bit confused is okay, especially when you think, wow, isn't she wrong? And then later on I think, oh my gosh, I was wrong. And you're like, I caught that before she ever said it. That should feel good, that you're tuned in enough to recognize a mistake when you see it. Okay, so now we're going to be converting these to z-scores. I just mentioned to you that we don't have a sign on a standard deviation, so we want to talk about negative and positive standard deviations. We call them z-scores. A z-score that's negative is to the left of the mean, and a z-score that's positive is to the right. And so in this question it says, if your score on a next statistics test is converted to a z-score, which of these z-scores would you prefer? -2, -1, 0, 1, or 2, and why? Well, a 0 z-score means that you were exactly at the mean. So you're right in the center of the data for that. So I wouldn't really, it wouldn't be terrible, but that's not probably where you'd want to be. anything with a negative z-score means you were lower than the class mean, so that's kind of bad. And so if you want the best possible one, you'd want to be over here at the highest possible z-score, because you're getting further and further to the right. That means a higher and higher score. So the z-score of 2 is the most preferable, because 2 is the standard deviation above the mean and would correspond to the highest of the 5 different test scores. Better z-score, better test score. Okay, the height of 69 inches, Marvin was the shortest president of a particular club in the past century. The club presidents of the past century have a mean height of 72.3 and a standard deviation of 1.7. This club is strange and they measure all their presidents, but we're just going to accept that. What is the positive difference between Marvin's height and the mean? So if you subtract Marvin's height and the mean, you're going to get the positive difference. So he was shorter, 69 inches. Oh, you know, let's switch over to mine. We'll change the numbers, but that's okay. I want to be able to work this out on paper. And 11, 12. Dun, 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 dun. Okay, so number 1, what is the positive difference between William's height? My numbers are slightly different. He's 64 inches tall here, and the height and the mean was 68.1. So the positive difference is 68.1 minus 64. Oh, I'm not going to do anything else, but just get 4.1. All right, and the difference is how many standard deviations? Well, the standard deviation that we had was 1.9. So I can take 4.1 and divide by 1.9, and that's going to tell me how many standard deviations that he was. So I'm going to do that, 4.1 divided by 1.9. And to the 2 decimal places is what they say, so 2.16. All right. And so the z-score, well, this is his z-score. The z-score you're going to find equals the x that you were given minus the mean, which is the x bar, divided by the standard deviation. And I don't know why they had us give the positive difference, but they did. Because on his, if we put his first, we actually get a negative. So his z-score is negative 2.16. I think it's confusing the way they did it. But let me show you something. Weird, they have it shown as positive. Let's just talk about this for a second. Here is the mean, and that has a z-score of 0, right? The mean here is 68.1. Here is 2 standard deviations back, and here is 2 standard deviations to the right. This guy is 64 inches tall. So if this is 68, 64 has to be on the left. In fact, it's showing us it's 2.16. So it would be somewhere to the left of the 2, right, would be 64 inches. So his z-score here is negative 2.16. You'd have to be taller than 68 inches to have a positive z-score. So the fact that they're showing... Oh, I see. They did show it. Okay, I was going to say, what the heck? Okay, this is how we found this. And then we said, but wait a second, his z-score's got to be negative because he's to the left of the mean. Z-score here is 0. Here's the z-score of 1, of negative 1 and positive 1. Z-score positive 2, negative 2, and he's a little bit to the left of that. Is he unusual? Remember what 2 standard deviations out are? 95%. I've drawn it wrong twice, but I've been saying it right many times. So 95% of the people are going to fall between negative 2 and positive 2 for their z-scores. he is even to the left of that. Since he's not in that 95% range, that means that he's unusual. He's unusually short for a president of this particular club that measures that. All right, let's go on to number 13. IQ scores are measured with the test designed so that the mean is 103 and the standard deviation is 18. Consider a group of IQ scores that are unusual. Where the z-scores that separate the what are the z-scores that separate the unusual IQ scores from those that are usual? I'm reading the same thing twice, I think, but let me slow down. What are the z-scores that separate the unusual IQ scores from those that are usual? What are the IQ scores that separate the unusual IQ scores from those that are usual? Okay, I guess we're talking about lower and greater. So consider a value to be unusual if the z-score is less than -2 or greater than 2. So all I have to do is say a z-score of 1 would be the mean plus 18 and a z-score of 2 would be plus 18 again. So if I add 18 twice onto my mean, I get the higher boundary, which is 139. Okay. If I wanted to find the lower one, which I probably should have done first, I'm going to subtract 118, which is 85. And then subtract it again. The reason I'm doing it this way, this is sort of a cumbersome way, but I want you to see what's actually happening. We're taking off 18 every time we talk about a standard deviation. And so what this looks like is that right here we have a z-score of 0 and our mean was 103. When I have a standard deviation of 1 and a standard deviation of -1, I have 121 and I have 85. When I have a standard deviation of 2 and -2, then I have 67 over here and 139 over here. And those are the scores that correspond to those z-scores, right? So a z-score is just a standard deviation with a sign attached to it, really. So I have 139 to the right and I have 67 to the left. Of course, I didn't answer that question right? I answered this. What are the IQ scores? Okay, so I didn't read that. I read that twice, but still didn't see the difference. Hopefully you're like ready to smack me around. I was going to do another video after this, but maybe I shouldn't. My mind is not really working. This is what I just answered. The IQ scores are 67 to 139. The lower z-score boundary is -2, and the upper z-score boundary is 2. I showed you that over here, but I didn't answer that question correctly. All right, and then that's where they're getting -2 and 2, and then 67 and 139. So we did that, but like spaz, not cool. So they already told you the z-score, so that kind of already gave you the boundaries. So I don't know why they're. It's a weird question to me, but anyways, because I saw those, I didn't think they wanted those, but I could have read the whole thing and known. Anyways, add 1 to get 1 standard deviation or 1 z-score up, add 2 standard deviations to get 2 z-scores up, and so forth. So if you said, oh, the mean value for the IQ test was 103 and I was 2 standard deviations above that, you get an IQ of 139, which is very high. All right. Let's see if I can get through number 14 and not make a mistake. One of the tallest living men has a height of 213 centimeters. One of the tallest living women is 202 centimeters tall. Heights of men have a mean of 171 centimeters and a standard deviation of 4. Heights of women have a mean of 158 centimeters and a standard deviation of 7. Relative to the population of the same gender, who is taller? In other words, is she taller for a woman or is he taller for a man? What we're going to do to find their z-score is to take their height minus the average and then divide by the standard deviation. So for the man, he was 213 minus the average 171 divided by the standard deviation of 4. And for the woman, she was 202 inches minus the average for women of 158 and divide by 7. And those two values are going to tell you what their z-scores are. And the taller person is the person who has the z-score that's different. His z-score, wow, 10.5. So obviously way out there, right? 3 standard deviations in either direction cover 99.7 of the population. He's 10 standard deviations away, so he's got a huge standard deviation z-score. Okay, 202 minus 158 divided by 7 is 6.28. Or 6.3 if we go to one decimal, 6.3, just doing that one. So she's tall, 6 standard deviations away is tall, but he is even taller because his z-score is higher. So the man is relatively taller because the z-score for his height is greater than the z-score for the woman's height. All right, interesting. All right. This is going to be the same thing, which is a relatively better score of 74 on a psychology test or a score of 53 on an econ test, and then they go about giving the mean and standard deviation of each, and you're going to figure out the z-scores and then decide which is which. I'm not going to do that again. Okay, number 16. Below are 36 sorted ages of an award-winning acting award winner. Okay, that didn't make sense to me for a second. I'm really out of it. Find the percentile corresponding to age 48 using the method prescribed in the textbook or presented in the textbook. So we want a percentile of 48. Round to the nearest integer as needed. So that's going to require a lot of entering stuff into your calculator. Not that sweet, but we'll go back and do it over here. This is number 16, and we've got 10 problems left. Sometimes, I don't know if StatCrunch works in here. Sweet. If you open StatCrunch, it just puts it all in there, and you can just do this on without having to enter in your calculator. I didn't even know StatCrunch worked in Math Excel. I thought it only worked in my math lab. Sweet. So then we can go to summary stats, columns. We want this one, which is the only one we have in there, and we want to find all of that stuff, compute. And it shows us the mean and the variance and the standard deviation and the standard error. So when you were entering those other ones and I was putting it in and we were having to find the variance, take the standard deviation, square it, it's done for you. Isn't that cool? I'll go through that again because I did it kind of fast. Go to stat, go to summary stats, go to columns, and then it tells you to pick the column because you might have more than one column of data, but we only have one. So just double click on it, it puts it over there. So it's going to do it for that one column. And then I'm not going to ask it to put in nothing else special. Here's what it's going to show me. It's going to show me all this stuff. And I could choose more, but I'm just going to choose that they show me that stuff. And then I'm going to say compute. And then it's going to give me all of that stuff. Sweet, right? So that's how I'm going to find that data. Let's go over and show you how to find the percentile given the method presented by the book. What we want to do is we want to find all the number of values that are less than x, and then find the total, but divided by the total number of values, and then times 100. So what we want to do is sort this list. Maybe it's already sorted for us. I think it is. So if we want to find, for this problem, x equals 53, there are 36 sorted ages for award-winning actor. Find the percentile corresponding to the age 53%. Yeah, so we're going to figure out where's our 53, which is here. There's a couple of them. We can see there are 21 values less than that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 20, 21 values less than that before we hit the 53. And the total number of values are 36. So you're going to see we have 21 values less than that divided by 36 values more than that times 100. 21 divided by 36 times 100 gives you 58. So the age of 53 is in the 58th percentile. All right. So if it's sorted, I thought it wasn't. So I'm all happy because I don't have to worry about that. Let's go back to my page and we can just do that pretty quickly. We have also 36. Whoops, we have 36. So we're going to divide by that total number of data values. We're talking about the number 48. Remember, there's 10, 11, 12, 13, 14, 15, 16, 17 values, and then that are below 48 because that's the value that they gave us. And then we times that by 100. That's just moving the decimal over 2 places. So we do 17 divided by 36, and we get 0.4722. And then we move the decimal point over twice to get to a percent. So that's what the times 100 does. And then it's to the nearest integer, so they just say it's 47%. Okay, so that's that. And now this is different because it's saying find the percentile that's corresponding to the age 22. So here's the 22 age, and we want to know what percentile that is. So it's kind of using this formula, which this formula was the number below our particular number divided by the number total of the total values times 100 equals the percent. And what we want to do now is we want to figure out, oh, this is the same. Oh my goodness, I'm seriously. So we're going to do that again. There's 3 below. There are 36 total times 100. We're just going to go 3 divided by 36 is 0.083. Well, when I times that by 100, it takes it over, so I get 8.3%, and to the nearest integer, it's just 8. I don't know. I slept pretty well last night. It's still early in the day. I don't know what's happening, but I think the other one. Now this is the opposite thing that I was thinking was going to happen. Below are 36 sorted ages of an award-winning actor. Find the 30th percentile using the method presented in the textbook. So we want to find the 30th percentile. Now what we're talking about is we do know that this is going to equal 30, right? And we know that there's a total of, times 100, we know there's a total of 36 values. And so we're interested in this. How many values were there below that to get us to the 30th percentile? So let's take a look at how the book did it. But that's we know now what the answer of 30% is, 30 percentile, because that's the number that they give us down here. But let's see what the book shows us as the method of choice. This one they're asking is for the 60th percentile. And so the first step is converting from a percentile to arrange the data from lowest to highest. And this one's already sorted, so that's good. L is going to be K divided by 100. N is times N, where N is the total number of values, and K is the percentile being used. So in this case, we have the total value of 36 values, and the percentile for this problem was the 40th percentile. And so if we plug into that, we find out what our number was, 14.4. And so they told us that L was 14.4 when we solve it. So we want to go to the one higher than that. So we go, there's 10, 11, 12, 13, 14.4. So we need to go up 1 from that to the 15th. And that's where we get to the 43. So we always go, if it's 14.4, we need to go up to the next highest one, right? So we can do this one. Oh, let's do the one on my page since it's written out. Let's solve for this problem. If you were to solve for V using your old algebra skills, this is times 100, so I could divide both sides by 100. That would go away, and I would get that. And then what would you do after that? You'd have V over 36 equals 30 over 100, and then you'd multiply by 36, right? And so your V would be 30 divided by 100 times 36. That's the same formula they gave us. They used L instead of V or whatever. But what I have is 0.3 times 36. 30 divided by 100 is where I got the 0.3. And that gives me 10.8. And so if I go 10.8, I need to go one higher to the 11th place to find my number. So there's 10, and then one more would be, I'm right there, which is 35. Okay, so L equals K over 100 times N is the formula that they gave. K being your percentile, which is given right here, 30. And N is the number of values that they gave you, which is N. So this is K, and this is N, and then just plug in to find that. When they ask you for quartiles, third quartile, first quartile, it goes like this. In the middle of your data, this is the minimum, this is your maximum, this is your median, and that's also the second quartile. That's the halfway point. There's quartiles dividing up into 4 parts. Here would be your first quartile, and over here would be your third quartile. That is dividing your data up into 4 equal parts. So there's 25%, this is at 25%, the median is 50%, the quartile 3 is 75%, and then your maximum is 100%. Over here you have 0%. So that's just a way, a quartile of 3 just is 75th percent. So if I was going to use this formula again, I would take K, which is 75, divide by 100, and 24 values are right here. So I'm going to do 75 divided by 100, which is 0.75, times 24, and I get 18. Well, what happens when you have the exact number? Before we saw one where you get a decimal. Let's see what happens here. If I go 18 places, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If I go 18 places out, and then I go 19 places out, I get 2 numbers. When I get an exact whole number here, what I want to do is take that number and the one next to it and find the average. And so if I take 64 plus 66 and divide by 2, that gives me the number. So if I have a decimal, which is the nicer one, because then you can just go up to the next value, that's great. But if you get an exact whole number, then you want to find the average of those 2 numbers, the number that you land on and the next one, find the average, and that gives you the 75th percentile, quartile, third quartile, 75th percent. All right, so that's done. All right, so now I want to talk again about those values, the minimum, the maximum, the quartile 1, quartile 2, quartile 3. Those are some of the numbers that show up when you do the stat calculations. So let's do the 5-number summary. And since I kind of didn't know what was available to you, I want to go do it now. This is number 20. And they've got this little thing right here. So let's dump this into StatCrunch. Sweet. Okay, so then I'm going to go to Stat, Summary Stats, Columns, and I'm going to use the first column. That's the only column I have here, and I'm going to go Compute. And here's our 5-number summary over here, sort of a little bit messed up, but it's pretty easy to see. What we have for our lowest minimum in our 5-digit summary is 4. That's our minimum. I'm going to write those down because it's different for mine because I have that. But then the next one is the quartile 1, and quartile 1 is 8620. The third one is median, which is back to the left a little there, 10,058.5. Then we have our quartile 3, which is 11,431, and finally we have our max, which was 11,895. That's called our 5-digit summary, and you can find that using StatCrunch just like that without having to enter all that, which is sweet. So what I said was that our minimum was 4, and the maximum, you can see these are already in order, was 11,895. The middle value, or the median, is the 50 percentile, and that one was 10,058.5. And then the quartile 1 is the data that's 25% of the way, 8620. And the quartile 3 is the data that's 4 over, and that's 11,431. And so I didn't have to do any work. I let the computer do that. That's my 5-number summary, which is sweet. Oh, sorry. Oh, round to the whole number. I didn't read the directions. This one. Yeah, it's 59. And anyway, I put a decimal instead of a comma. Oh, for heaven's sakes. I got these numbers from the calculator, right? 11,431, 11,895, 10,058.9. Well, 58.5 rounded to 10,059.4. Well, maybe they don't like a comma in there at all. Let's see. Yep, that's bad. They should take it with a comma or without a comma. That's really bad. So the box plot, you can look at the notes to hear more about box plots. But the box plots, we plot them, and it shows those numbers. So all of these should end at about 11,895, and that's this ending bar down here. And that looks, they all look about like they do. Well, this one, it's hard to tell, but this one, yeah, I mean, I think so. The smaller number over here is the minimum. That's this line. So we have the minimum here and the maximum over there, and that should be at 4. So this one's out because look where it's at. This is ridiculous. The minimum is not that, so forget about that one. And then the median, the box shows the quartile 1 at the left side, the median in the middle, and the quartile 3 at the right side. The median and the quartile 2 are one and the same. So we should be at about 8,620. So let's see. This looks like about 6, 7, 8, 9, 10, 11. Yeah, 8,000 would be here. And this isn't it because it's not there. 6, 7, 8,000. That looks about right. 7, 8, that looks about right. So far, our minimum and our maximum and our quartile 1 for B and D look pretty good. So let's go on to our median is 10,059, 6, 7, 8, 9, 10, 59. That looks pretty close. 7, 8, 9, 10. It's just below that, right? If I go straight up, our median doesn't show correctly. So you're just going to see which one of those actually has those numbers plotted. Remember, far left is your minimum, far right is your maximum, and then you have quartile 1, quartile 2, quartile 3, quartile 2 being the median as well. To determine the 5-number summary and construct a box plot. It's the same type of question. Remember, you can put that into StatCrunch. Stat, summary stats, columns. Choose that column, which is the only one that you have. Then click compute. Your minimum is 81. Quartile 1 is 88.5. Median is 94. Quartile 3, 98.5, and your maximum is 109. So you can get the ranges in the middle there, and these aren't in the right order, but that's what you're getting. Now remember that they ask you to type integers or decimal. Oh, and this one they do okay with that. And also you saw that they didn't like mine because I had a comma in there. So, you know, it's frustrating, but you'll figure it out. I do. Same thing, we're going to go find those 5-number summary and then pick the graph that matches it. When a data value is converted to a standardized scale representing the number of standard deviations, the data value lies from the mean. We call the new value a blank. We just did this. It's a standard deviation with a sign attached to it. Once you attach a sign to a standard deviation, we call it a z-score. That should be our choice in there. Whenever a data value is less than the mean, then what happens? So that's a good question. If you have a data value that's less than the average, you should expect to see what kind of a z-score, positive or negative. Well, when you're less than something, generally we think of it as negative. So it should make sense in your head that a negative z-score means you're less than average. Whatever you're looking at has a less than average mean. In the modified Boxplots, we didn't talk about interquartile ranges. I don't even think they asked for that. So we should do that. And then is the next one about that too? Are they both about interquartile ranges? Which the following is not a value in the 5-number summary? Well, the 5-number summary, as you know, is a minimum, a maximum, quartile 1, median, which is quartile 2, and quartile 3, but it doesn't have the mean in there, so that's not it. So the only one we haven't talked about is this interquartile range. I gotta flip that over to paper because I can't just talk about that without showing you something. Okay. I don't want to stop recording. I want to come over here. There we go. So when you have a box plot, and I'll just draw one here. Let's say my minimum value is 10, and my maximum value is 753. And then along the way, so I have this here, here, and then I have this, looks like that, here, here, and then it goes, that's kind of what it looks like. Remember here I have also a median value. So my scale is probably off pretty badly, but let's say that my quartile 1, this is my minimum, this is quartile 1, this is quartile 2 or median, this is quartile 3, this is my max. So my quartile 1, let's have that be 82, and my quartile 3 will have that be 370, and my median will have be 150, and forgive the bad drawing. But when I want to find the interquartile range, that's just the difference between the third quartile and the first quartile. When I subtract that, so I would just take 370 minus 82, and that would give me the difference between this value and that value. In other words, I want to know the range of that box. So if I take the range of the box, I get 370 minus 82, and that gives me 288. And then I want to know, do I have any outliers? Is this number out here, 753, is that an outlier? Well, what I do is I take my quartile 1 value and I subtract 1.5 times the interquartile range. And so that looks like 82 minus 1.5 times 288. that's going to give me a minimum value that I would accept as normal on my box plot. So I'll take 82 minus 1.5 times 288. And that would take me to negative 350. And my minimum value is 10, so I'm clear. I mean, anything down to negative 350 would be normal. My third quartile plus 1.5 times 288. And that means I would have 370 plus 1.5 times 288. And that would be the maximum allowable value before I would say that I had an outlier. And that's 802. And I have a value that's 753, so it's okay. This gives you the range from the interquartiles, using interquartiles, and what's the range of, oh, I should have wrote IQR here, but I wrote the actual number. That's the range of values that you're okay with, and you say, okay, I don't have an outlier because my maximum value was 753, then I'm good. All right, so if you were looking at people like how many Facebook friends does somebody have, and you have, you were looking at people that have as few as 17 Facebook friends, and then, a lot of people that have in the 50s, 60s, 70s, hundreds, 200s even, but then there's somebody that has 4,053. When you find that box plot like this, you then calculate this, you might find that somebody that has thousands of Facebook friends would be an anomaly or an outlier. And that's what can happen. I don't know if on the one that they did, they just wanted you to answer the question, what is an outlier? But so now I've told you an outlier is something that is above quartile 3 plus 1.5 times IRQ, or below quartile 1 minus 1.5 times the interquartile rule. But I just wanted to show you how to do that, even though I probably did it in the notes, but it's good to know that. All right, this one's gotten obscenely long, so let's stop. Have a great day, and I'll see you next time.